Alright, I've got two final topics of lift I want to talk about before we're done. First is spinning balls. So if you've got a baseball that you throw into the air and you throw it so when you release it, it starts spinning. It's traveling through the flow field, say in this direction, and you release it with backspin so that it rotates. What happens is as that ball spins around, there's a no-slip boundary condition, and it drags the airflow along with it, right? So as it drags the air around with it, on the bottom of the ball, the airflow is colliding with the fluid flow, so you get an increase in pressure. And then on top of the ball, it's dragging the air in the same direction as the fluid flow, so you get a decrease in pressure. So a way to look at this is what you've done is induced circulation around the ball, and you get low pressure above it, high pressure below it, and that causes lift. So by spinning a ball, you can generate lift. And lift isn't always up, right? In this case, it's solely a function of the axis of rotation. So in this case, the lift is up, but if I spun it sideways, I could get the ball to curve left to right or right to left. And if I threw it with downspin, with spinning in the other direction, I could get the ball to drop. So I would have downward lift. The other thing this does, which isn't readily apparent, is it actually stabilizes the boundary layer and decreases drag. This is further, both of these effects are further enhanced by roughness. So we talked about this with a golf ball, just how roughness can decrease the drag of a golf ball. What I didn't mention before is that rotation also plays a big role in this effect, and that also decreases drag as well. So golf balls, they travel about 170 miles an hour. They rotate a ton, 3,000 to 8,000 RPM. And the dimples aid in this effect of decreasing drag and increasing lift. If you've played golf or watched golf, you'll know that it's called shaping your shot, controlling how that ball curves as it approaches the green is a huge part of golf. So striking the ball so that it's hooking or slicing, that's applying spin to get the ball to curve one way or another. And then also getting backspin on short chips to get it to stop near the hole. Those are all huge parts of the sport. Tennis balls are fuzzy. I think we talked about that already. One of the reasons they're fuzzy is to decrease drag, but as you rotate them, you can get the ball to curve as well, so it increases lift as well, and that's hitting drop shots and floaters are really important in tennis. Obviously, the best example of this is baseball. There's no sport where curving is more important. And the seams on a baseball, although they're historical in nature, they serve a vital purpose. They provide that roughness that really helps increase lift and decrease drag. So if you throw a curveball, you spin it as you release it from your hand, and you get a huge amount of RPM on the ball. And you can actually get it to move left to right, a really good thrown curveball, 17 inches from mound to plate, which is pretty amazing. Another pitch that's really interesting from fluid dynamics or fluid mechanics standpoint is the knuckleball. This is thrown deliberately with hardly any rotation. And what happens is you get a really unstable boundary layer. And remember when we talked about those oscillating Kármán vortexes? They, if you remember, we just looked at that in sort of 2 dimensions, but if you think about that in 3 dimensions, you have a vortex forming behind one side of the baseball, and that low pressure zone will cause that ball to move in that direction, and then that'll peel off, and then another one will form somewhere else. The ball will move in that direction, and then another direction. So what happens is if you throw this right, you can get that ball to kind of float around in a random fashion. And then the seams also add a little bit of randomness to it as they spin in and slowly spin in and out of play. Fastball obviously is thrown as fast as you can, but spin also has a huge impact on it. They're thrown with lots of backspin, so the ball, not only is it moving fast, but it doesn't drop like you'd expect it to. It stays level. In fact, thrown really well, it can even rise between the mound and the plate. Okay, the last thing I want to talk about is sailing. So, to propel a boat forward, you put up a giant sail to catch the wind, and the wind pushes you along, right? No, actually, that's not at all how a sail works. In fact, sailing is quite complicated. Sails are actually airfoils. If you look at wind flowing in this direction, let's say we have a boat with a sail and we just have it set up kind of like a parachute, so it's just collecting the wind and the wind is pushing the boat along. That's actually the slowest way you can sail. You can't move any faster than the wind. In fact, because of inefficiencies, you move at some fraction of the wind speed. But if you travel in the other direction, if you travel perpendicular to that and you set up the sail properly, the sail acts as an airfoil. So it bends the air backwards in relation to the boat. In other words, the air is pushing the boat forward. And when you do this, your boat can actually travel at faster the wind speed, which seems a little crazy. How can you harness the wind and actually travel faster than the wind itself? But when you use your sail like an airfoil, that's what happens. Now, sailing is full of all kinds of jargon. If we look at the different directions, if you travel with the wind, that's called a run. If you travel 45 degrees, that's called a broad reach. If you travel 90 degrees, that's a beam reach. And you can even travel into the wind, and you can't get much closer than 45 degrees into the wind, but traveling into the wind is called a close haul. Now the run, that's your slowest direction that you can travel. Turns out if you want to travel downwind from one point to another, the best way to do it is with a series of broad reaches where you zigzag back and forth. You will actually get to your destination faster. Even though you'll travel more ground, your velocity is so much higher that you'll get to your destination faster than if you just go on a run. And keep in mind, with a close haul, you can travel upwind, but again, you have to zigzag back and forth to do it. Now, the fastest you can travel is on this beam reach. So 90 degrees to the wind, you can travel as the fastest as possible, and that is quite commonly faster than the speed of the wind itself. Now, sailing as a sport is immensely complicated. There's all kinds of things to think about just in terms of the fluid mechanics and the boat itself and the angles and the changing weather conditions, and you have to put all that together to be a good sailor. So it really takes a lifetime to learn how to be a good sailor. One of the things that they have to do is constantly trim their sails, is what it's called. And what that means is a sailor has to constantly be shaping this piece of fabric so it behaves like an efficient airfoil. And that has to do with not only the size sail that you're using, but how far you've pulled it in, how you've adjusted the stays on it so that you shape it. And this is all going on outside as the wind is changing direction and speed. So it's a very complicated business. And then finally, most sailboats don't use single sails, but they use two sails, a mainsail and a jib. The jib is typical to a slat on an airfoil, on an aircraft. The jib is actually used to direct wind over the mainsail to prevent boundary layer separation. So you can maximize your lift without causing the wing to stall. And then finally, I just said that you never want to do a run, but there are cases where the wind is so strong where it does make sense to use your sail like a parachute. Those are called spinnakers. It's a specially designed sail, and it has the added benefit of actually lifting your boat out of the water and reducing your drag. So there are cases where this becomes advantageous.